So in the last video, we talked about how I'd found a set of numbers, a class of numbers that reduced to a power of 2 after 2 steps through the odd Collatz function. And it was apparent that there wasn't a simple pattern to it. And I mean, you've got a first example and a second example, right? You've got your first step through that 101 pattern, and then your second step through where you're finding numbers that are behaving this way. And so I think naturally when you're doing math, you wonder if that generalizes to a third step and then a fourth step and all that sort of stuff. But I think that gets a bit ahead of what's going on. And so I wanted to examine the second step a little bit more first. So, in decimal, I'm just going to write the first couple examples of these numbers. So we have 3, 13, 53, 113, 213, and then 227. And then it goes on. I posted a program on my GitHub. The link is in the last description. So you can download it, duplicate these results, and see why these numbers behave the way they do if you want. But yeah, I'm going to write these out in binary so we can start to examine them in a bit more detail. There's a very famous paper by a mathematician from Calgary, actually well, he wasn't from Calgary originally, but he did a lot of his work here, Richard Gray, called Don't Work on These Problems. And one of the ones that he lists is the Collatz conjecture. And since I'm not a mathematician, I think I can hardly disagree. It's fun. I enjoyed it. Not that, I'm the next Einstein or anything, but math should be fun, and I really enjoyed monkeying around with it. So 1, 0, 1, 0, 1, 0. There we go. I think that's right for 213, and then 227 is. So we've got this list of binary numbers, and I want to start dividing up the digits in the binary numbers in a way that we can find a pattern. So with the number 3, I'm just going to split it in 2, right? I'm going to say right down the middle is 1 and 1. And then for 13 here, I've got 1, 1, 1, 0, 1. And so this is the first sort of step where you can see something interesting going on, right? So if we recall from our previous example, our previous class of numbers, here we've got 1, 0, 1, right? So this is our 1 step pattern, right? And we can think of 13 as 1 and then 3 zeros, right, in binary, plus the pattern 1, 0, 1, right? So here I've got, I'm adding my first step pattern to this other number, and I'm getting a new number 13 that behaves in a way where I can predict how it's going to behave in the first step of the Collatz conjecture. And so if we look at another number like 53, right? 53 was 1, 1, 0, 1, 0, 1, right? And so again, I'm going to notice that alternating pattern of 1s and 0s, right? I'm going to see what I've got here. So I know that when I multiply by 3 this number and then add 1 to it, I'm going to have some sequence of zeros in my even number. And I can predict how many zeros are going to be. I can predict precisely, right? So if we take 53 and we triple it, right, I'm going to have this. and I go 1, 1, 1, 1, 1, 0, 1, 1, 0, plus 1, right? And then this 1 here is going to cascade through all of these. It's going to flip all of these ones into zeros. So now I know here that I had 1, 2, 3, 4, 5, and here I've got 1, 2, 3, 4, 5. So I've found, a way to predict how part of my number is going to behave in its first rotation through the Collatz conjecture, right? So I can take any binary number. I can take a binary number that starts with a 1 and has some pattern of 1s and 0s and ends in a number. So I can predict how any odd numbers, right, like is going to behave. So if I have, 1 and then my number ends in 1, 0, 1, well, I know I'm going to have 3 divisions by 2 afterwards, right, because of this lovely pattern here. I know, for example, that if I have 1, 1, well, the pattern breaks immediately. So here I have 1, 0, right, and here I have 3 zeros. And then I know that if I have some string, of some alternating 1s and 0s, right, like a really long string here of 1s and 0s all the way to the end, and then the pattern up here is slightly different. Well, I know that when I chuck this number into the odd Collatz function, right, I know that all of these are going to become zeros. So there's a hint here with what we've got, that there's, the possibility that we can assemble a number so that it'll behave a certain way in the Collatz function, so that we can say, well, after the first step, I know I'll have 12 divisions by 2 because there was this alternating pattern of 1, 0, 1, 0 of 12 digits. It's a bit more complicated than that, but right now, hopefully it's clear that there's a lot of possibility here, right? Like we're looking at numbers that we can sort of assemble and we can put together in certain ways. We don't know if all possibilities, if we can make a number behave however we want, but we know that there's something really interesting going on here.